Hello, everyone. Welcome back. We are going to finish up section 3.5, which is the first derivative test. We're well into this section, so we have the basics of how this works by now. So we're going to go ahead and get started. The directions for this problem was find the local extrema. And we have to do it using the first derivative test, it said. Now, local extrema is talking about localized maxes and minimums, the bottoms and tops of these hills, these turning points of my graph. Those are my local extrema, and we're going to find those using the first derivative test. Now, the first derivative test is just a fancy name for that number line analysis that we do with the derivative. So let's get started on this one. To find any local extrema, you got to figure out the x values where those might happen, and those are called critical numbers. So the first thing you want to do is find any critical numbers. To find any critical numbers, you have to take the derivative and set it equal to 0 and see if there are any domain restrictions that pop up after I get done taking the derivative. So let's start with the first thing. Let's take the derivative of that and set it equal to 0. The derivative of this is going to involve a general power rule, which you would have learned earlier on in this chapter. So let's do the general power rule. We have the power rule, C times R, negative 6 times 2, which is negative 12. 3x squared minus 12 to the 2 minus 1 power, so we have a 1 understood to be there. Now, when you're doing the general power rule, you have to remember you have to multiply by the derivative of the inside function. The inside function here is 3x squared minus 12, so the derivative of that is 6x. This is our general power rule. You do the power rule part, and then you multiply by the derivative of the inside. Now, the derivative of that 9 over here by itself is 0, so I'll put that there for emphasis, but you don't have to write the 0. This is my first derivative, and I'm supposed to be setting this whole thing equal to 0 so I can solve for the critical numbers. Now, let's look at this. I might need to clean this up before I do anything else with it. Let's take this 6x and kind of move it up front next to that negative 12 there, so that I have negative 12 times 6x times that 3x squared minus 12. Negative 12 times 6, let's multiply that together. So 12 times 6 is 72. So this becomes negative 72x times 3x squared minus 12. This is my derivative function. And it's a little cleaned up from where we had started with it. Now, since I'm supposed to be setting this equal to 0 so I can solve for critical numbers, I'm going to leave this in its factored form. This is already kind of pre-factored. I have one function times another, and we've seen before when you have something that's factored and set equal to 0, you can set these individual parts equal to 0. So that is to say, it would be going in the opposite direction of progress to multiply this term into these two terms. You just have to factor it right back out. So we're in a good place right here to go ahead and solve this by setting each of these little pieces, the minus 72x, setting that equal to 0, and setting the 3x squared minus 12 equal to 0, so that we can solve for our critical numbers here. All right. So when I have negative 72x equals 0, if you solve this algebraically, you would have to divide both sides by negative 72. But over here, 0 divided by negative 72 is still 0. So from this angle, this route, I get a critical number. One of them is going to be x equals 0. From this route here, I'm going to solve algebraically. I'm going to add that 12 to the other side. I get 3x squared equals 12. Divide both sides by the 3 so that you get x squared is equal to 4. And then square root both sides. Don't forget the plus or minus. We have square root of 4 is 2. I have plus or minus 2 as a result there. So as part of setting my derivative equal to 0, I now have 1, 2, 3 critical numbers. So let's list those out just to give them a name. I have 3 critical numbers, and they are x equal 0, x equal 2, and x equal negative 2. Positive 2 and negative 2 from over here. I have 3 critical numbers, which means that I have 3 candidates for maybe being corresponding to these local extrema. But that's a maybe, we don't know. That's why we have to do the next thing, which is the number line analysis. Before I continue on with that, though, I do have to ask myself, when I look at the derivative, are there any domain restrictions that kind of pop up? That's because if there was a new domain restriction that kind of popped up in my derivative, then I would have to catalog that and put that on the number line as well. That would also be a critical number. But when I look at this actually doesn't have any square roots in it, for example, so I don't have to worry about restrictions on x making a root negative. So no square roots to worry about. And I don't have any denominator of this expression that I have to worry about being 0. So that is to say that this is very non-problematic in structure. It has no roots, it's not a fraction. I do not have any domain restrictions that come out of this. So that is to say, are there any new domain restrictions for the derivative? We say no, and then we go, okay, let's move on to our number line analysis. Our number line analysis, number line is supposed to represent the domain of our function here. All the way to the left is minus infinity, and all the way to the right is infinity. And on this number line, all you want to put on it is your 3 critical numbers, but make sure that you put them in order. The most negative one goes first, right? -2, and then 0, and then +2. So I have to test all around these values by taking test points and plugging them into the derivative. By doing that, I'm going to figure out if each of these numbers correspond to a maximum, a minimum, or maybe neither one of those, but we'd know. So what you do is you take a test point in each little region in between those. So I'll have 1, 2, 3, 4 test points you choose, and you can pick any number as long as it's in the middle between there. So let's say that we pick -3 to be in this interval. Let's say that we pick -1 to be in this interval. +1 is my test point between this interval, and maybe +3 is my test point for that interval. Now, once you pick these numbers that are in between your critical numbers, you're going to plug those into your derivative. Now, this is where I like to use my calculator. Let's put our derivative function, this fella, into my y equals. Let me darken that up so you can see it. There we go. Let's put our derivative function into our y equals. That's way it's easier to plug stuff in. So I have -72x times 3x squared minus 12. Put it in there exactly like that. That's my derivative function. And I'm going to plug my test points into it. So I'm going to go over here to my table. And remember, last video I showed you the trick to get this to work. Plug in your test points. So I'm going to plug in -3, enter, -1, enter, 1, enter, 3, enter. And I get values out for these, and these are values of the derivative, right? I'm plugging these numbers into the derivative to get these numbers as a result. So the sign on these tells me a lot about what my function's doing. When I plugged in -3, I got a positive result. I got 3,240. If I get a positive result out, that means that my function's increasing on that interval that I pulled -3 from. So I'm going to put increasing there. At my -1 test point, I got a negative value for the derivative. So that tells you that your function is decreasing. So I'm going to put that there. But checking my 1, I got a positive value for the derivative, 648. So that means my function is increasing there. And then when I look at my 3, I got a negative value for that. So that means my function is decreasing on that region I pulled 3 from. So this tells you an awful lot about your function now. Not only does it tell you where it's increasing and decreasing, etc., but we're supposed to be drawing conclusions about my critical numbers, and I have 3 of them. These are potential maxes and mins, so I got to figure out, based off of what's going on either side, what's happening there, if anything. For a -2, I see that my function is increasing and then decreasing on each side of -2. It's going up first, and then it turns around and comes back down. So if it's going up and turns around and comes back down, that means that one has to correspond to a maximum. So then I come over here and I focus on my 0 there. What's going on either side of 0? Well, on this side of 0, my function's going down. It's decreasing, 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 and then it'll turn around, come back up. It's increasing on this side, decreasing on this side, increasing on that side, going down, then going back up. That means that 0 has to correspond to a minimum. What's going on at 2? My function is going up. It is increasing. And then on the other side, it goes back down, decreasing. Gotta be a max. So now I know that there is a local maximum corresponding to -2 and +2. There's a local minimum corresponding to x equals 0. And these are two different maximums, by the way, two different bumps. So maybe our graph came back up and I have 2 bumps on it, 2 turning points that result in a maximum. So that can happen. All right, let's wrap this up. They usually want you to write these as points. So let's write this out. We have local maximums, 2 of them, at -2 comma something. I'm going to find that out in a minute. And +2 comma something. I've got to find the corresponding y values for those. So for that, you take your -2 and your 2 and you plug it back into the original function, because the original function cranks out y values, right? I'm going to plug these up there. So while I'm at it, let's go ahead and take care of my minimum so I can punch all of my y values out at once. I have a local minimum that will be at x equals 0. So I have a local minimum point at 0 comma something. So I'm going to find the y values for each of these 3 points. I'll have an actual point value here. So I'm going to come back to my y equals, and I'm going to put in my original function now. -6 3x squared minus 12 squared plus 9. I'm going to go to my table, and now I'm going to put in -2, enter. I get a y value of 9. 2, enter. Get a y value of 9 again. And 0, enter. Get a y value of -855. That one's kind of down there a ways, but there's our points. I have 2 local maximums here and here, 1 local minimum right there. We got it. All right, let's scooch on here. Problem D. Here's our function. 2x to the 5 halves minus 320x minus 12. And then they give us a hint here. It says find the domain of f of x first. And that's actually a helpful hint here. Let's look at this. This is 2x to the 5 halves. Now remember, fraction exponents are the same as roots. They're just a different way of writing a root. It's writing the root as a power as opposed to an actual root symbol. So if we were to just come over here to the side for our own viewing and rewrite this as its root equivalent, this would be the square root of x to the 5th. 2 times the square root of x to the 5th. The 2 in the bottom is the root part, and the 5 is the power part on the x. So we have a problem here. Square roots, you can't take the square root of a negative number. Like square root of like -1, not allowed. Or anything that results in this being negative in here can't happen. So it looks like since I have a 5th power here, if I were to plug in -1, for example, I'd have -1 to the 5th, which is still -1, which then I'd have a square root of a negative number. So because this is an odd power, any negative number I put in here is going to still make it odd after I take the 5th power of it. So it looks like x cannot be any negative number. Because it'll make me have to take the square root of a negative number. That is to say that the domain of my function has to be that I only consider x so long as x is greater than 0. X is positive. So this is our way of saying that you can only plug in positive values for x. We needed to know that because when I do my number line analysis, just like I did up here, my number line is not going to be negative infinity to infinity anymore. I'm actually not allowed to consider the negative numbers on my number line analysis because of this domain restriction. So we'll come back to this, but that's how it will affect us going forward. I'll have half of a number line I'm going to look at, all of the positive parts. Anyway, now that we've done that and we know what we're dealing with, let's get to the point, which is I want to find any local maximums and minimums of this thing, which means I have a familiar process ahead of me. I have to find the derivative of this thing and set it equal to 0 because I want critical numbers. So let's take the derivative of this. This is going to be a power rule. 2 times 5/2 x to the 5/2 minus 1, which is 3/2. The derivative of 320x is 320. And the derivative of negative 12 is 0. So you end up with the derivative is, these 2's will cancel, 5x to the 3/2 minus 320. That's my derivative. And while we're here, let's ask ourselves the question that we have to anyway. Okay, now that I've taken the derivative of this, are there any new domain problems? Like, I already knew what part of the domain problem was. Part of my domain problem, I have x can only be positive. So I've already got something I'm looking at. Is there anything else that comes up after I take the derivative? Well, now that I've taken the derivative, this is x to the 3/2, which means it's x to the 3 square root. It's square root of x cubed whenever you convert this to its root equivalent. This still has the problem that if you plug any negative numbers, it would still be negative inside, and then I'd have to take the square root of a negative number. So it looks like this derivative has the same exact domain restriction as the original function did. It's not any different, and it's not any new. So there's nothing new to comment. The previous domain restriction is all that there is still. So when we ask the question, are there any new domain restrictions, we go no, and then carry on. So our carrying on means that we're going to set this thing equal to 0 and solve for x. Let's add the 320 to the other side. 20. Divide by 5 on both sides. So I have 320 divided by 5 over there. Let's see what that is over here. 320 divided by 5 is 64. And now here's where it might be good to go ahead and convert this to its root equivalent, just so it's a little easier on us to solve this thing. So if this is square root of x cubed, the thing I can do to solve for x is square both sides. So if you square this side, the root goes away, and then I got to square that over there. So what's 64 squared? 64 squared is 4,096. And then I have to cube root that, right? Because this is x cubed. To get x by itself, you cube root both sides. So let's see what that is. Cube root. Oh, and since this is an odd root, when you cube root, you don't have a plus or minus thing. It's only when it's even roots that you have to do plus or minus. So no pluses and minus this time. It's odd. I have cube root. Uh, 4,096 is 16. And the way I wrote this on my calculator, by the way, is cube root is 4,096 to the 1/3 power, right? That's its fraction equivalent. So instead of trying to find a cube root button, I always just write it in as a power. So we get 16 there. That is a critical number. It is quite possibly a local max or a min point, or it corresponds to there. That might be where one's at. So what do we have to do? We have to do our number line analysis now. So let's come over here, since I wasted all of this space. I have a giant block of white space here. Let's do our number line analysis. Now remember, I don't have a number line that goes from minus infinity to infinity anymore. I have a number line that starts at x equals 0 and goes to infinity because of this domain restriction. So I have to start at 0, go to infinity. I've got half of my number line I'm working with this time. All right, so on this chunk of number line, I have to put my one and only critical number. There it is. And then I carry on doing the stuff I usually do. Let's pick a test point in each region there. So pick a number between 0 and 16. So 10, sure, why not? Pick a number between 16 and infinity. Let's do 20. And what do you do with those? You plug those into the derivative, that thing, because the derivative is going to tell you whether your function's increasing or decreasing. Let's go back to our y equals, erase our old stuff, and put in our derivative function. 5x to the 3/2 minus 320. Go to our table, delete all our old stuff. Remember, all you have to do is hit the delete key to go to your old data. And I'm going to plug in my 10. And when I plugged in 10, I got this value for the derivative. So I'm plugging 10 into the derivative, and I got negative 161.9. That means that my function is decreasing at 10. I get a negative value for the derivative, decreasing at 10. So I'm going to put here, function's decreasing. Now let's plug in our other test point, 20, do 20, enter. And I get a positive value for the derivative, 127, which means that my function is increasing there. So I have a conclusion to draw. As soon as I know that x equals 16 is a critical number, that's a special value. If there is going to be a local max or a min, that's got to be where it is. That's the only spot it can happen. That's what makes a critical number special. Because if there's going to be a max or a min, it's got to happen at a critical number. That's it. So I got one candidate for being a max or a min. So when I come over here, do I have either one of those things happening? I have that my function is decreasing, it's going down on the left of 16, and it turns around and it's going back up on the other side. Down on one side, up on the other. That means it's got to be a bottoming out. There's got to be a minimum corresponding to x equals 16. So let's write it out. We have that there is a local minimum at x equals 16. So we have a point that we can find, x, y, 16 comma something. So if I want a y value, so I can plot this on a graph, I'm going to take 16 and plug it back into the original function. So I'm going to clear out my y equals there, put in the original function, 2x to the 5/2 minus 320, x minus 12. There we go. Go back to our table, delete our old data, and I'm going to put in my x equals 16 so I can find the y value there. Since you're plugging 16 back into the original, this gives you a y value of negative 3084. That point is way down there. Might be hard to plot that one if you're drawing it, but that's where it is. That's where our local minimum is. It's a turning point way down on our graph. So what we'd say in words is that the local minimum occurs at 16, and the local minimum is negative 3084. Let's scooch on over to the next one. Last page. We're almost there. We got 2 more. We have f of x is 25x squared plus 4 over x. Now, how does this function look different from the last several? This one's a fraction, and those are always more fun, right? It's got a lot more going on. And they give us a nice little reminder here. It says put domain restrictions from the original function and the derivative on the number line. Well, that's a good idea. The unfortunate thing about rational functions, that is ones that looks like a fraction like this, is there could be what I call, quote, bad values of x. any value of x that you might plug in that causes the bottom to be 0, those are domain restrictions, right? Those are bad x values. So if I'm looking at this fella here, I have, if I try to plug in x equals 0, I would get a 0 in the bottom, which can't happen. So right off the bat, I know that no matter what I do, x cannot be 0, like ever, 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 ever. There's a big hole in my graph at 0. There's probably a vertical asymptote going on there. But whatever I do, x can never be 0 because it causes the bottom of my function there to be 0. That said, what was our whole goal here? Our whole goal of this problem is to find local maximums and minimums. So why do I care about this domain restriction? It's like, well, we are going to do a number line analysis, and if x cannot be 0, that means that I have to put this on a number line just so I can skip over it. So this, any domain restrictions like this have to go on your number line as at default. They have to go on there. But even though they're on the number line, this can never be a local extrema. It's probably going to be a vertical asymptote instead. But what some domain restrictions can never be, from the original function anyway, domain restrictions of the original function can never be a local max or min. So we just know we're going to have to put that on a number line once we get to it. Okay, so now that we know that part, I need to find critical numbers. That's always our first task, because critical numbers are my candidates for being these maximums and minimums. They're the only ones I'll have. Now remember, I have critical numbers that come from two places. One, where you set the derivative equal to 0 and solve. We've been doing that a lot already. And two, if there are any new restrictions on f prime that the original function does not have. So I know that x equals 0 is a restriction of my original function. That guy can never be a local max or a min. But, if I took the derivative and my derivative had a new domain restriction that wasn't 0, now that one would be a critical number. And that one could be a max or a min. I know it's weird, but it's a thing. Any new domain restrictions of f prime would be a critical number. So let's see what happens. Let's just see what happens. I've got to find critical numbers. So either way, I've got to take the derivative. So let's focus on taking the derivative. This is a fraction. We're going to take the derivative using the quotient rule. So let's go ahead and do that, and we'll simplify it. So the quotient rule is the bottom times the derivative of the top, and I'm going to do this here in one go instead of making my usual lists that I do. Bottom times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared. So we get here, and I do have to simplify this a tad because I'm going to set this equal to 0, right? So let's take this x and multiply it by 50x. That gives me 50x squared. And let's distribute this minus sign to both of those terms. I get minus 25x squared minus 4. And this is all divided by x squared. Let's combine our like terms. I've got 50x squared minus 25x squared, so that's 25x squared. 25x squared minus 4 divided by x squared. Here's my derivative, simplified down. I haven't done anything with it yet, but I mean, it looks nice. So I'll box that just so I can see it later once I need it again. I'm going to take that, and I'm going to set that equal to 0. And when you set this fraction equal to 0, the whole point about fractions is that I'm not allowed to let the bottom equal 0. So the only thing that'll make this whole thing equal to 0 is if the top is set equal to 0. So this is what I tell my class. Whenever you have a fraction and you're setting equal to 0, just take the top and set that equal to 0, because that's really the only thing that can be 0, right? The bottom's not allowed to be 0, domain restriction, that whole jazz. So take the top and set that equal to 0 instead. That gives you 25x squared minus 4, this part, set equal to 0. And then this is a bit easier to solve. If you add the 4 to the other side, divide both sides by 25, and square root both sides, making sure to do plus or minus. Now the interesting thing about, well, the nice thing about square roots, rather, is that the square root does kind of distribute in a way to the top, so that becomes the square root of 4 over the square root of 25. So I get plus or minus 2 over 5. I've got two critical numbers. X is positive 2/5 and negative 2/5. So these are the critical numbers I get by taking the derivative and setting it equal to 0. That takes care of the first part. The second part that I mentioned earlier is that I have to ask myself, are there any new domain restrictions of my derivative that the original didn't have? So when I look at my derivative function, there it is. If you're looking at that and you ask yourself again, what would be a bad x value to try to plug in? Well, it would be 0, because you can't have 0 squared. You can't have the bottom being 0. And what is the offending x value? It's still x is 0. So for the derivative function here, x equals 0 is still a problem. There is not any other different x value that becomes a problem after I've taken the derivative. The value of x that was bad is still bad, and there's not any new ones. So since there's no new bad x values, I have no other critical numbers. But I do want to point out, if there was a new bad x value here, then that would be a critical number, and I'd have to put that on a number line, and that would be potentially a max or a min. It didn't happen this time, and it's very rare that it does happen, but it happens occasionally. We have to keep an eye out for that. So let's start our number line. Now our number line, I can plug any other x values into this thing except for 0. So my number line's minus infinity to infinity again, but I do have this big old hole at x equals 0. And I'm going to make sure to write down here, this is a bad x value. So even though this x value 0 is on the number line, this guy can never, ever be a local max or a min, no matter what's going on either side of it. We don't care. It's never going to be anything. X equals 0 is just here because we have to put it there, but it can never be a local max or a min. Put your two actual critical numbers here. We've got negative 2/5 and positive 2/5. So those are my potential maximums and minimums. And I've got to find test points on either side of those, making sure to dodge my 0 here, and figure out what's going on. So let's pick test points to the left and right of my negative 2/5 and to the left and right of positive 2/5, just so I can see what those are, if anything. This is where I'm going to go to my calculator, and remember we plugged test points into the derivative, so I'm going to put the derivative function into my y equals line. 25x squared minus 4 divided by x squared. I go to my table, clear out my old data. Now pick a number between minus infinity and negative 2/5. So whatever, negative 5 is far enough down that line. So I picked negative 5 from down here, and I got a positive result from the derivative. So I would say on this little region here, my function is increasing. Now pick a number between minus 2/5 and 0. It's got to be in this little region here, in between the critical number and 0. And so a number between minus 2/5 and 0 would actually be negative 1/5. So let's plug in negative 1/5. Negative 1 divided by 5. and we get a negative result for the derivative. So that means on this region right here, my function is decreasing. Now let's scooch on, hop over our 0. I've got to pick a point between 0 and positive 2/5 so I can test this side of this critical number. Pick positive 1/5. 1 divided by 5. We get negative 75 again. So that means that right here on this little region, my function is decreasing. And then pick a number between 2/5 and infinity. So we might do positive 5 or whatever. We get positive result for the derivative that time. So we'd say my function is increasing on that region. All right, my two candidates. What's going on there? We have my function is increasing and then decreasing on either side of negative 2/5. It's going up first and then it turns around and goes back down. So that means that this fellow there has to correspond to a local max. If I scooch over here to 2/5, my function is going down. It's decreasing. It's going down on this side, and then it turns around and goes back up on the other side. Down and then up, which means that 2/5 has to correspond to a local min. All right, let's write our conclusions. I have a local minimum and a local maximum. One of each. I'm going to plug these two x values back into the original function up here so that I can get the y values for those points. I'm going to write this as a point, both parts. I have negative 2/5, comma y, and positive 2/5, comma y. I'm going to clear out my y equals and put my original function there. Go to my table and put in negative 2 divided by 5 and 2 divided by 5. Then we get, for negative 2 divided by 5, I got a negative 20 y value. And for 2 divided by 5, which is 0.4, I got positive 20. So we're done with this problem. We got our answer. There's my local extrema. Now, as a side note, I do want to mention that x equals 0, we mentioned it was bad. It could never be a max or a min. But so it doesn't matter what was happening on either side of 0, because 0 is never going to be anything regardless. So this could have been decreasing, increasing, or increasing, decreasing, or increasing, increasing. We do not care what is happening on the left and right of 0, because 0 is not allowed, or it can't be a local extrema. So don't read into checking out whether we have a change in anything here, because 0 is a domain restriction. It's never going to actually be a local max or min. All right, last one. We have the same reminder that we had above. Here's our function. I'm supposed to be finding local maxes and mins, right? But I have possible domain restrictions because this is a fraction. And so I have to always look at my fractions and go, okay, what's a bad value of x for this guy? What value of x might cause my bottom to equal 0? And to that we go, well, it looks like 0. If I plugged in x equals 0, the bottom would be 0. So we have to say here that x cannot be 0. That's my domain restriction so far. I can plug any other value of x I want, but not 0. So this again is going to follow me through onto my number line. It is a domain restriction, but this is never going to be a local maximum or min. Okay, so now that I know that, let's take the derivative and try to find any critical numbers, because those are possibly my local max or min. So I got to find critical numbers. Take the derivative of that. Quotient rule. Quotient rule is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the square of the bottom. We do have to simplify this. We have 2x times x there, which is 2x squared. And then I have, this is multiplied by 1, so nothing happens from that direction, but I gotta distribute the minus sign here. This will be minus x squared plus 1. Combine like terms, 2x squared minus x squared is x squared. So we get, this is my simplified derivative. Looks nice. And I'm supposed to be setting that equal to 0 and solving for critical numbers. So while we're here, let's do our analysis. Remember, critical numbers also come up if there are any new domain restrictions on my derivative. So my original domain restriction is x can't be 0. Is that still the case for my derivative? And it looks like, yeah, I still can't plug in 0 there because I'd get 0 squared in the bottom. So 0 does follow through and continues to be a problem for my derivative. And there isn't any other different x value that becomes the bad x value. It's still x equals 0. There's no other new ones. So since there's no new ones, that's not 0, there's no critical numbers from that angle, and there's nothing to comment on. So we move on. Let's take that whole function and set it equal to 0. X squared plus 1 over x squared, we set that equal to 0. Now, similar to what we were talking about up there, when you have a fraction equal to 0, the bottom's not allowed to be 0, right? That's where domain restrictions come from. So the only thing that sets fractions equal to 0 is if you set the top equal to 0. So let's do that. We have x squared plus 1 is the part that's getting set equal to 0. So let's try to solve this and see where it goes. We take this 1, subtract it to the other side. We get x squared is negative 1. And then we square root both sides, taking care to do plus or minus. And then we end up with plus or minus the square root of negative 1. And so we have to look at this and notice something. I can't take the square root of negative 1. We're not dealing with imaginary numbers in calculus. It's not a thing. So what this is no solution. This is not a real, this is a non-real answer. So I get no solution from this route. So what does that mean? The whole purpose of this angle was that I set my derivative equal to 0 to find any critical numbers. So if I'm going through the motions and I write here, no solution means that I got no critical numbers. No critical numbers. And we already said that we didn't have critical numbers from new domain restrictions either, because there's no new bad x values. Critical numbers come from setting the derivative equal to 0, or if there's any new domain restrictions. And neither one of those yielded anything. We had no new domain restrictions, no critical numbers here. And so since there's just seems to be no critical numbers at all from any direction, there cannot be any local extrema. Local extrema has to correspond to critical numbers, period. If you don't have any critical numbers, you don't have any local maxes and mins. End of the story. So if I get no critical numbers, which I do, then that's it. We would say there's no local extrema. We don't even got to do a number line analysis. If we don't have any candidates, we don't have any candidates. That's it. So that's the answer to this one. There's no local extrema because there's no critical number, actually. So we're done with this one. This happens occasionally, too. All right, so we are done with section 3.5, the first derivative test. Good luck with your homework, and I'll see you next time.